Have you ever just stopped and wondered how we actually know the distance to a star? Or, the weight of a single atom? It all boils down to one single fundamental thing: measurement. Today, we're going to dive into this incredible quest for precision. We'll explore how we, as a species, learn to measure everything from our own backyards to the absolute farthest reaches of the universe.
So yeah, let's just jump right in with that big one. How in the world do you take a ruler to a star? I mean, it sounds completely impossible, doesn't it? Well, stick with me here because the answer involves some seriously clever thinking, and we are going to break it all down. This one question, it's really the key to understanding our place in the whole cosmos.
And this is why it all matters so much. Physics, which is really just the study of nature itself, is fundamentally built on this one idea. If you want a precise description of anything, you have to be able to measure it. Without numbers, without units, without accuracy, well, science is just philosophy. To truly get a handle on the universe, we have to measure it.
But for the longest time, this was a massive problem. Just imagine trying to build something like an international space station, when one team's blueprints are in feet and pounds, and another's are in centimeters and grams. It was a total world of confusion. You had these competing systems, like the British FPS and the Gaussian CGS, and it made doing universal science incredibly difficult.
So, to fix all this chaos, the world desperately needed a single universal language just for science. It was time, really, to create some order out of all that mess.
And here's the solution. Back in 1960, the General Conference of Weights and Measures introduced something called the International System of Units, or just SI for short. You can think of it as a super smart, rationalized version of the metric system, and it quickly became the global standard for all of science and technology. Finally, everybody was speaking the same language. And the real genius of the SI system is its beautiful simplicity. The entire universe of measurement, everything we could possibly want to measure, is built on just 7 fundamental units. You've got the meter for length, the kilogram for mass, the second for time, and a few others. Think of these 7 units as the alphabet of science. From these 7 letters, we can spell out literally any other measurement we could ever need.
So for instance, when you're measuring something as huge as our solar system, using meters is, well, it's just clumsy. The numbers get ridiculously big. So scientists came up with the astronomical unit, or AU. It's defined simply as the average distance from the Earth to the Sun. It gives us a much more convenient ruler for measuring things on a planetary scale. But then, when we look beyond our own solar system, even the AU starts to feel tiny. So we need even bigger units. That's where the light year comes in, the distance light zips through in a year. And the parsec, which is even bigger, at about 3.26 light years. It really just goes to show you how mind-bogglingly huge the universe actually is.
And just to show you the incredible range we're talking about, let's flip from the biggest scales to the absolute smallest. This is a shake. It's one of the smallest practical units of time we have, clocking in at 10 to the power of -8 seconds. It was a term that nuclear physicists used, and it's just a fantastic reminder that precision matters at every single scale you can possibly imagine.
Okay, so we've got our units, we have this universal language, but how do we actually use them to measure things that we can't possibly reach, like a mountain or a star? Well, that required some truly ingenious methods. Let's start with the classic, triangulation. Say you want to know the height of a mountain. You don't have to climb it with a giant tape measure. Nope. All you have to do is measure your distance to its base on flat ground, and then measure the angle from where you're standing up to its peak. A little bit of high school trig, and boom, you've got the height, all without ever leaving your spot. Pretty clever, right?
But we can get way more high-tech than that. To get the exact distance to the moon, we use the laser method. Scientists literally fire a powerful laser beam at special reflectors that the Apollo astronauts left up there on the moon's surface. Then they just time how long it takes for that little pulse of light to travel there and back. And since we know the speed of light with incredible precision, we can calculate the distance with amazing accuracy.
And this all brings us right back to our original question. How do you measure the distance to a star? The answer is this incredibly clever trick called the parallax method. Here's how it works. An astronomer will look at a nearby star from one side of Earth's orbit. Then they wait 6 months for the Earth to travel to the opposite side of the Sun, and they look at the same star again. Against the background of really distant stars, that nearby star will look like it's shifted just a tiny bit. By measuring that tiny shift and knowing the diameter of Earth's orbit, they can calculate the distance. We're literally using our planet's own orbit as a gigantic ruler.
Now, all of these methods are incredibly precise. But, and this is a really important but, none of them are perfect. And that leads us to a final, really crucial idea in science, learning to embrace the uncertainty of uncertainty.
To really get what uncertainty is, we first have to be super precise with our language. Take mass and weight. In everyday life, we use them like they're the same thing, but in physics, they're completely different. Your mass is the actual amount of stuff you're made of. That's the same whether you're on Earth or the moon. But your weight, that's the force of gravity pulling on your mass, and that changes depending on where you are. So you see, precision starts with having clear definition.
Okay, so when scientists talk about error, they don't mean they made a mistake. An error of measurement is just that unavoidable little difference between the absolute true value of something and the value you actually measure. No measurement, no matter how careful you are, is ever going to be perfectly 100% exact. And these errors, they can come from a few different places. You have systematic errors, which come from your tools, like a scale that's not calibrated right. Then you've got random errors, which are just due to unpredictable little fluctuations in the environment. And yeah, okay, sometimes they're gross errors, which is just a nice way of saying human carelessness. Good science is all about finding and minimizing every single one of these as much as humanly possible.
So here's the crucial point to all this. Uncertainty isn't failure. In fact, it's the exact opposite. It's a hallmark of good science. When a scientist states the result as a number plus or minus some uncertainty, that's an honest statement. It's them telling you exactly how confident they are in their number. It's science being as rigorous and as truthful as it can be.
And that kind of leaves us with a final thought to chew on. If every single measurement we ever make, from the width of a piece of paper to the distance to a galaxy, comes with this little bit of uncertainty, what does it really mean to truly know something? It turns out that the quest for precision is also a quest to understand the very limits of our own knowledge.